Software is absolutely everywhere, right? I mean, our phones, cars, finances, medical kit, it runs pretty much everything.
We totally rely on it.
But you know that moment, that really frustrating feeling when the software you need just, well, it does work.
Oh, yeah. And the consequences can be, well, they can be pretty significant. Our source material for this deep dive really hammers this home.
Right.
It talks about the whole spectrum, from just irritating losses of time or money.
Which is bad enough.
Exactly, to serious damage to a company's reputation. And sometimes in those really critical systems, it can even lead to physical injury or worse.
Which just makes the whole question of how we build software that actually works reliably, safely. It makes it incredibly important.
Absolutely.
So this deep dive, we're focusing on understanding the core ideas behind that whole effort, the fundamentals of software testing.
And we're using, let's say, a foundational text as our guide today. It lays out the essential what, why, and how of testing pretty clearly.
Okay, so our mission together is to cut through any confusion, really dig into what software testing is, why it's so vital, and break down the key principles and activities. So by the end of this, you listening should have a really solid grasp of this, well, this crucial part of the tech world. Let's unpack it.
Sounds good. So starting right at the beginning, what is software testing at its core?
Yeah, the definition.
Well, the source defines it as a whole set of activities, and the aim is twofold: assessing the quality of the software and, critically, reducing the risk of failure when it's actually being used.
Reducing risk.
Yeah.
That feels key.
It is. It's about finding defects, sure, but also evaluating all the different pieces that go into making software. They call these work products.
Work products, like what exactly?
Things like the requirements documents, the design specifications, the actual code, user guides, you name it.
Gotcha. And the material, it seems quick to point out a common misunderstanding, right?
Yeah, exactly. That testing is more than just running the software, clicking buttons, seeing what happens.
Which is just one part, test execution.
Right. Test execution is just one activity. Testing itself is much broader. It includes a whole bunch of activities, and it's meant to be integrated throughout the entire software development life cycle, not just tacked on at the end.
Okay, that makes sense. It's a process, not just an event.
Precisely. And within that broader scope, there are two concepts you've probably heard, but it's worth, getting the distinction really clear, like our source does: verification and validation.
Ah, yes, verification and validation. Always tricky.
Well, verification basically asks, are we building the system right? Like, does it meet the technical specifications? Does it match the requirements written down?
Okay, building it right according to the plan.
Exactly. Whereas validation asks, are we building the right system?
Ah, the right system.
Yeah. Does it actually meet the user's needs? Does it work for the stakeholders in the real-world environment it's supposed to operate in?
So does it solve the actual problem?
That's a great way to put it. And testing, proper testing, involves doing both of those things: verification and validation.
And it's not just about running the code, you said.
No, definitely not. The source also covers static testing. That's testing without executing the software.
How does that work?
Things like reviewing documents, requirements, designs, even the code itself without running it, doing walkthroughs with the team, using static analysis tools that scan the code for potential issues.
Okay, so finding problems just by looking, essentially.
Oh, analyzing, yeah. Both static testing and dynamic testing, the execution part, are vital components.
Which really highlights something the material emphasizes, that testing isn't just some rote technical task.
Not at all. Tools are definitely used, but the core of testing is described as deeply intellectual.
Intellectual? How so?
Well, it requires specialized knowledge, analytical skills,
Yeah.
critical thinking, even creativity, you know, and systems thinking, understanding how all the parts interact.
Right. Seeing the bigger picture. It's not just pushing buttons.
It really is a craft. And the specific goals of testing, they can actually vary quite a bit depending on the context. The source lists a whole range of typical objectives.
Like what kind of objectives?
Well, evaluating those work products we talked about, requirements, designs, code, or deliberately trying to cause failures.
Trying to break it.
Kind of, yeah, to find the hidden defects underneath. Another goal is ensuring adequate coverage.
Coverage? You mean like you've tested enough of it?
Exactly. Making sure you've tested enough of the software or enough of the requirements. And of course, reducing the overall risk of poor quality.
That risk reduction again?
Always comes back to risk. Plus, verifying compliance, making sure it meets specified requirements or contractual ones, legal, regulatory.
All the rules it has to follow.
Right. And providing good information to stakeholders so they can make informed decisions like, is this ready to ship? Building confidence that the software will actually work.
Okay.
And ultimately, validating that the software is complete and actually functions the way the people who need it expect it to.
That's quite a list. And you mentioned context matters.
Hugely. The source notes that what's most important among those objectives can really shift. It depends on, say, what specific thing you're testing, the level of testing, like component versus system, the identified risks, the development model being used, agile, waterfall, whatever, and even business factors.
So context is king.
Absolutely. It dictates the focus.
Okay, so testing is this broad intellectual activity. It covers verification, validation, static, dynamic, lots of potential goals. But let's tackle another pair of terms people often confuse. The source makes a point of separating testing and debugging.
Yeah, that's a really, really important distinction. The source is crystal clear. They are not the same activity.
How are they different then?
So dynamic testing is what can trigger a failure, a visible problem caused by an underlying defect. Static testing, on the other hand, can sometimes find the defect itself directly without anything failing.
Okay, so testing finds the problem or triggers a symptom. What happens next?
That's where debugging comes in. Once dynamic testing triggers that failure, the debugging process starts. It involves reproducing the failure consistently.
Which can be hard sometimes.
Oh, definitely. Then diagnosing it, figuring out why it failed, finding the actual defect in the code or wherever it is, and then finally fixing it, modifying the software to remove the defect.
So find, diagnose, fix. That's debugging.
In a nutshell, yes.
And once the developer thinks they've fixed it.
You've got to test again. Two types of testing here. First, confirmation testing.
Confirmation, checking the fix worked.
Exactly. Often done by the original tester, the source suggests, making sure that specific problem is gone. But then, just as importantly, you need regression testing.
Regression testing, making sure the fix didn't break something else.
Precisely. It's checking for unintended side effects. You fixed one thing, did you accidentally mess up something over here?
Got it. Debugging fixes. Testing confirms the fix and checks for new problems. What if static testing found the defect originally? Was debugging different then?
It's simpler, yeah. Since there wasn't really a failure caused by running the code, debugging is more straightforward. It's just about finding and removing the defect from the document or code where static testing spotted it. No need to reproduce or diagnose a runtime failure.
Okay, that makes sense. Which brings us right to the big why. Why is all this testing necessary in the first place?
Well, the source frames testing as a really critical type of quality control. It helps projects actually hit their targets, stay within scope, on time, deliver the required quality, all within budget.
So it's about project success, fundamentally.
Exactly. And it's not just for dedicated testers. The source points out that anyone on a project team can benefit from using testing skills and thinking.
Interesting. So what are the key ways testing contributes to that success, according to the material?
Well, one huge one is just cost-effective defect detection. Finding defects means they can be removed by debugging.
Which improves quality.
Indirectly, yes. But testing also provides a more direct evaluation of the software's quality at different points. It gives stakeholders objective information.
Like actual data to decide if it's good enough.
Right. Information they need to make smart decisions like, is this feature ready? Should we release this version?
It provides visibility.
Visibility and evidence. And the source makes another really interesting point. Testing can act as a kind of indirect representation for the users.
How so?
By understanding user needs and perspectives, and then testing the software against those needs, testers can sort of act on behalf of the user throughout development. It's often more practical than having actual users involved every single step of the way.
Like an advocate for the user experience within the team.
You could see it that way, yeah. And then, of course, there are the external pressures.
The must-dos.
Right. Testing is often absolutely required to show you're meeting contractual obligations or legal requirements or specific industry regulations, compliance.
Makes sense. Okay, let's tackle another pair of terms that often get jumbled. Testing versus quality assurance, QA.
Oh, yeah, that's a classic mix-up. The source definitely highlights that people use them interchangeably, but they really mean different things.
So what's the difference according to this?
Testing, as we've been discussing, is described as being product-oriented. It focuses on the software itself, and it's corrective in nature. Its activities aim to find defects in the product to achieve a certain quality level. It's a major form of quality control.
Okay, product-focused, finding problems. What about QA?
QA, or quality assurance, is described as process-oriented. Its focus is on the how the software is built and tested, and it's preventative.
Kind of.
Yeah. The core idea is that if you have good, well-defined, consistently followed processes for development and testing, you'll prevent defects from getting into the product in the first place, or at least reduce them significantly.
So QA is about making the system of building software better.
Exactly. Improving the development and testing processes themselves. And the source also frames QA as everyone's responsibility, not just a separate QA department.
So, just to summarize, testing finds defects in the thing you build. QA tries to improve the way you build things so fewer defects happen.
That's a great way to put it. And the source points out that test results feed into both.
Ow.
Well, for testing, the results obviously lead to fixing the specific defects found. For QA, those same results provide valuable feedback on how well the processes are working. Are we seeing lots of defects of a certain type? Maybe our coding standards process needs improvement, that kind of thing.
Got it. So testing informs QA about process weaknesses.
Exactly.
Okay, that clears things up. Now let's zoom in on the life cycle of a problem itself. The source talks about errors, defects, failures, and root causes. How do they all connect?
Yeah, think of it like a chain reaction, as the material describes it. It starts with humans. We make errors, mistakes, basically.
We're only human.
Right. And those human errors can produce defects, faults, or bugs in the software or related documents, the work products.
So the mistake creates a flaw.
Precisely. Then, if that defect in the code is actually executed, or if a defective requirement leads to wrong code, it may cause a failure. A failure is when the system doesn't do what it's supposed to or does something it shouldn't.
The visible problem.
Yeah.
Error leads to defect, leads to potential failure.
That's the sequence.
Why do those initial human errors happen? What causes them?
The source gives a few common examples, things like intense time pressure, maybe the system or the task is just really complex, plain old tiredness, or maybe someone just didn't have the right training or information.
Everyday pressures, basically.
Pretty much. And these defects they create, they can hide anywhere.
Whereabouts?
In the requirements docs, design specs, the source code obviously, but even in things like build scripts or test scripts themselves. And a really crucial point the source makes is that a defect introduced early, say a mistake in the requirements, if it's not caught early, it can cascade and cause more defects later on in the design and code.
A domino effect.
Exactly.
And you said a defect may result in a failure. Why may? Don't all defects cause failures?
Not necessarily. The source points this out. If a code defect gets executed, yes, it can cause a failure, but some defects only trigger failures under very specific, maybe rare conditions.
Like only on a Tuesday when the moon is full.
Sometimes it feels like that. Or maybe the conditions just don't happen in normal operation. And some defects might technically exist in the code, but actually never cause a failure in practice.
Interesting. So a hidden flaw might just stay hidden.
It's possible. And are failures always caused by these human errors leading to defects?
Good question. Is there anything else?
According to the source, yes. It mentions that environmental conditions can sometimes cause failures too. Things like radiation, strong electromagnetic fields. These could potentially cause failures, maybe by fighting a bit in memory or inducing a defect in firmware, for example.
Wow. Okay, so it's not always a programmer's mistake.
Not always, though errors and defects are the most common cause.
So we have error, defect, potential failure. Where does root cause fit into this picture?
The root cause is digging deeper. It's the original fundamental reason why the error happened in the first place, or why the defect was introduced and not caught earlier.
Getting to the real source of the problem.
Exactly. It's the underlying condition or situation that allowed the error to occur. Root cause analysis, as the material describes it, is about finding these underlying issues so you can actually prevent similar problems from happening again in the future.
So it's not just fixing the bug, but fixing the reason the bug happened?
Precisely. It's about systemic improvement, not just patching symptoms.
Okay, that chain error, defect, failure, root cause is much clearer now. Let's shift gears a bit. The source lays out 7 fundamental principles of testing. These sound like really core ideas.
They really are. They're presented as general guidelines that apply to pretty much all testing.
What's the first one?
The first, and maybe the most fundamental, is that testing shows the presence of defects, not their absence.
Okay, what does that mean practically?
It means testing can find bugs, and that's super valuable. But no amount of testing can ever prove with 100% certainty that there are no bugs left. You just can't test every single possibility.
So testing reduces the probability of undiscovered defects, reduces risk.
Exactly. It reduces the likelihood that nasty surprises are still lurking, but it doesn't guarantee correctness. It doesn't prove the software is perfect.
That's a really important kind of humbling principle.
It is, and it leads straight into the second principle. Exhaustive testing is impossible.
Meaning you just can't test everything.
Right. Except for maybe the most incredibly trivial pieces of software, trying to test every single combination of inputs, every possible sequence of actions, every environment. It's just not feasible. The number of possibilities explodes very quickly.
Infinite possibilities, almost.
Pretty much. So, since you can't test everything.
You have to be smart about what you test.
Exactly. This principle highlights why we need effective test techniques, why we need to prioritize our testing, and why risk-based testing focusing on the most important or riskiest areas is so crucial. You have to make choices.
Makes sense. What's principle 3?
Early testing saves time and money. This one feels intuitive, but it's critical.
Finding bugs earlier is cheaper.
Exponentially cheaper, according to the source. Finding and fixing a defect in the requirements phase, maybe through a review, that's relatively cheap. Finding that same defect after the software has been released to customers, the cost can be massive rework, support costs, reputation damage.
Right, because that early defect might have led to flawed design, flawed code.
Exactly, that cascading effect again. Fixing it early prevents all that downstream cost and effort. So the principle is, start testing activities, both static and dynamic, as early as possible in the life cycle.
Don't wait until the end.
Please don't. Principle 4 is that defects cluster together.
Cluster, like they hang out in groups.
Kind of, yeah. It's based on the Pareto principle, the 80-20 rule. The observation is that a small number of modules or components within a software system often contain most of the defects found, or are responsible for most of the operational failures.
Okay, so problems aren't usually spread evenly.
Typically not, and this is useful because it helps you focus your testing effort. If you find a few bugs in one area, it's often a good idea to test that area more thoroughly, because chances are there are more bugs hiding nearby. It helps target risk-based testing.
Find one, look for its friends.
Sort of. Principle 5 is interesting. Tests wear out. It's sometimes called the pesticide paradox.
Pesticide paradox, like with insects becoming resistant.
Exactly the same idea. If you keep running the exact same set of tests over and over again, they become less and less effective at finding new defects. The remaining defects are sort of resistant to those specific tests.
So you need to change up your tests.
Yes. To find new bugs, you generally need to review and revise your tests, add new ones, keep them fresh, although the source does add a caveat. For automated regression testing, running the same tests repeatedly is exactly what you want to do. Because the goal there isn't finding new bugs, it's making sure existing functionality hasn't been broken by recent changes.
Okay. Different goal, different approach. What's principle 6?
Testing is context dependent. This
Yeah.
echoes what we said earlier about objectives. There's no single universal best way to test everything.
It depends on the situation.
Totally. How you test, the techniques you choose, the intensity, the documentation, it all needs to be adapted to the specific context. Is it a banking application or a video game? Is it safety-critical medical software or an internal website? The risks, the requirements, the technology, the team skills, they all influence the right testing approach.
One size does not fit all.
Definitely not. And finally, principle 7, which ties back nicely to verification and validation, the absence of defects fallacy.
The fallacy. The mistaken belief.
Right. The source calls it a misconception to think that just because you found and fixed lots of defects, or even verified that the software meets all its written requirements, that means the system will be a success.
Why is that a fallacy? If it meets the spec and the known bugs are fixed.
Because the spec itself might be flawed or incomplete, the system could perfectly implement every single requirement written down, pass all the tests based on those requirements, yet still fail miserably in the real world because it doesn't actually meet the user's real needs or the underlying business goals.
The validation piece again. Building the right system.
Exactly. Verifying against the specs isn't enough. You also need validation to ensure it's fit for purpose. Building a defect-free system based on flawed requirements doesn't help anyone.
Those 7 principles really paint a picture of testing as a thoughtful, strategic activity, not just bug hunting.
Absolutely. They provide a strong mental framework.
So we have the principles. How does this translate into, actual work? The source talks about a process, test activities, things called testware, and roles.
Right. Testing isn't just random. It's typically organized into a set of common activities that form a process. Now, this process has to be tailored to the context, like we said.
Context, again.
Always. And it's often iterative, especially in Agile, but there are these main groups of activities that usually happen.
Can you walk us through those main activities based on the source?
Sure. It often kicks off with test planning. This is the high-level thinking. Defining the objectives of the testing for this project or iteration, figuring out the overall approach you're going to take, considering constraints like time and budget. It answers the what's our strategy question.
Okay, setting the direction.
Exactly. And running alongside that throughout the process is test monitoring and control.
Monitoring and control sounds like project management.
It is essentially for the testing effort. It's about continuously checking, how are we doing compared to the plan? Are we on track? Are there problems? And then taking action, controlling the process to steer things back if needed or adjust the plan.
Keeping tabs on progress.
Right. Then, once you have a plan, you get into test analysis.
Analysis. What are you analyzing?
You're analyzing the test basis. Those documents or items you're basing your tests on, requirements, user stories, design specs, sometimes even the code itself. The goal is to identify what needs to be tested. What are the features? What are the conditions we need to check? You define and prioritize these test conditions, often thinking about risks.
So figuring out what to test in more detail.
Exactly, in a way that you could eventually measure coverage against. It answers, what should we test?
Okay, analysis identifies what then?
Then comes test design. This is where you get more concrete. You take those test conditions identified during analysis and you elaborate them into actual specific test cases.
Designing the experiments.
That's a good way to think of it. You figure out the steps to perform, the specific inputs to use, and crucially, the expected results. What should happen if the software is working correctly? You also identify necessary test data and any specific environment setup needed. Test design answers, how specifically are we going to test it?
Designing the how. And then you actually build the stuff you need.
That's test implementation. This is where you create or acquire all the necessary testware.
Testware. You mentioned that before. What is it again?
Testware is basically all the work products generated during the testing process, specifically to be used in testing. The source gives lots of examples.
Right.
The test plan itself, riskless, the test conditions and test cases you designed, test procedures, which might group test cases, any automated test scripts, the test data you need, setup scripts for the environment, basically all the supporting materials for testing.
Okay, so implementation is getting all that ready, setting the stage.
Exactly. Organizing test cases into suites, maybe scheduling them, verifying the test environment is ready.
And then the main event, test execution.
Right. This is the part most people think of as testing, running the actual tests according to the plan and schedule. Could be manual, could be automated, maybe continuous testing integrated with the build.
And comparing what happens to what you expected.
Precisely. Comparing actual results against the expected results defined in the test case. Logging everything passes, fails, analyzing any discrepancies or anomalies, and if you observe a failure, you report a defect.
Documenting the problems found.
Yes. And finally, there's test completion.
Wrapping things up.
Yeah. This happens at key milestones, maybe the end of a test level, an iteration completion, or before a major release. It involved activities like summarizing the testing, checking if exit criteria have been met, handling any unresolved defects or requirement changes.
What else?
Archiving the testware that might be useful later, maybe shutting down the test environment if it's temporary, doing a retrospective or lessons learned session to improve the process for next time, and creating a final test completion report for stakeholders.
It sounds like quite a structured process, even if it's iterative.
It provides a framework. And again, the source really stresses how context shapes all of this.
Right. Context affects how you do each step.
Exactly. Things like who the stakeholders are, the team skills, the business domain, is it high-risk finance or a casual game? Technical factors like the software architecture, project constraints, scope, time, budget. Organizational factors, the development lifecycle used, the tools available. All these influence your test strategy, the techniques you pick, how much automation you use, your coverage goals, how you report results.
It's always adapting. You mentioned testware examples like plans and cases. What else falls under that umbrella?
The source definition is pretty broad. any work product produced during test activities. So besides plans, cases, scripts, and data, it includes things like test logs generated during execution, the defect reports themselves, and that final test completion report. And it mentions the importance of managing all this testware using configuration management so you know which version of a test applies to which version of the software.
Keeping everything consistent. The material also talks about traceability, linking things together.
Yes, traceability is really important in testing. It's about creating and maintaining links between the elements you started with the test basis, like requirements, and the test where you create conditions, cases, scripts, and then the results of execution and any defects found.
Why bother making all those links? What's the benefit?
The source lists several good reasons. First, it helps you evaluate test coverage. You can clearly see, for example, which requirements are covered by which test cases and which aren't.
Okay, helps you see the gaps.
Exactly. It also helps you assess the residual risk based on test results. If tests linked to high-risk requirements are failing, that tells you something important.
Makes sense.
It also makes impact analysis much easier if something changes. If a requirement changes, traceability tells you exactly which tests might need updating.
Saves time figuring that out.
Definitely. It also supports things like audits or IT governance requirements, and it makes test reports much clearer for stakeholders because you can report status in terms of the original requirements or user stories they care about.
Showing progress against the goals.
Right. And overall, it provides valuable data for assessing the quality of the product, the capability of your testing process, and the project's progress towards its business goals.
So traceability isn't just bookkeeping. It provides real insight.
That's the idea. You can follow the thread from requirement all the way to test result and defect.
Okay, so we have the process activities, the stuff you create, testware, and the connections, traceability. What about the people? Who does all this? What roles are involved?
The source primarily identifies two main roles in testing: a test management role and a testing role.
Test management, like a test manager?
Could be, yeah. This role has the overall responsibility for the test process itself, leading the test team if there is one, and managing the testing effort. Their main focus tends to be on those planning, monitoring, control, and completion activities we talked about.
So steering the ship.
Kind of. And the material notes this role can look different depending on the context. In some Agile teams, these responsibilities might be shared more widely, whereas larger, more formal projects might have a dedicated test manager.
And the other role, the testing role.
This role is more focused on the hands-on technical and engineering side of testing. Their primary activities are usually test analysis, test design, test implementation, and test execution.
The ones doing the detailed test work.
Generally, yes. But the source is clear that these are roles, not necessarily rigid job titles. Depending on the project, the organization, the individual skills, different people might perform tasks from both roles, or one person might even cover both, especially in smaller teams.
So flexibility based on context again.
Always context.
Thinking about the people actually doing this.
Yeah.
What skills make someone good at testing? What does the source highlight as essential skills or good practices?
Well, there's a mix of skills. Obviously, foundational testing knowledge is key. Understanding techniques, processes, the principles we discussed. That's crucial for being effective.
Beyond the basics.
Personal qualities matter a lot. Things like being thorough, careful, naturally curious, methodical, having a really good attention to detail. These help testers find those subtle, tricky defects that others might miss.
The mindset is important.
Very. And then there are the people skills. Communication is huge.
Especially if you're the one finding problems.
Exactly. The source points this out directly. Testers often have to deliver unwelcome news about defects. People can sometimes be defensive or resistant. Confirmation bias is real. So testers need strong communication skills, active listening, and teamwork abilities to report issues constructively, manage perceptions, and collaborate effectively with developers, business analysts, everyone.
Diplomacy is a testing skill.
It really can be. What other skills are mentioned?
Analytical thinking, critical thinking, and even creativity are needed for designing effective tests and solving problems encountered during testing.
Creativity. That's interesting. Yeah, like thinking of unusual ways the software might be used or might fail. Technical knowledge is also important, especially for efficiency, understanding the system under test, using test tools effectively, and domain knowledge.
Understanding the business or user area.
Right. Understanding the context the software operates in, the user's goals, the business processes, that helps ensure the testing is relevant and focuses on what really matters.
Okay, those are skills. What about team approaches? The source mentions a whole team approach.
Yes. This is often associated with methodologies like agile or extreme programming. The core idea is that quality is everyone's responsibility, not just a specific test team's job.
So developers test, testers code.
Potentially, yes. Or at least team members collaborate very closely. Testers might pair with developers, business analysts get involved in defining acceptance criteria that become tests. The goal is to break down silos, improve communication, leverage everyone's skills, and build quality in from the start.
Sounds good. Does it always work?
The source notes it fosters collaboration and shared ownership, which is great. But it also suggests it might not be the best fit for every single situation. For instance, in highly regulated or safety-critical contexts, a greater degree of formal independence in testing might still be necessary or even mandated.
Which brings up the other practice mentioned, independence of testing. Having testers who are separate from the developers. What are the pros and cons there?
The main benefit highlighted in the source is effectiveness at finding certain types of defects. An independent tester comes in with a different perspective, different assumptions, maybe different cognitive biases than the person who wrote the code.
Fresh eyes find more bugs.
Often, yes. They're more likely to question assumptions the developer made or see things the developer might be blind to because they're too close to it.
Makes sense. What are the downsides of independence?
Well, the source points out potential drawbacks, too. Independent testers can sometimes become isolated from the development team, leading to communication gaps or delays. There can sometimes be an us versus them mentality, unfortunately.
An adversarial relationship.
It can happen. There's also a risk that developers might feel less ownership or responsibility for quality if they think, oh, the test team will catch everything. And sometimes the separate test team can be perceived as a bottleneck or get blamed if things go wrong.
So it's a trade-off again.
Exactly. And context matters. The material suggests that often the best approach involves multiple levels of independence.
Like how?
Like developers doing their own testing, unit testing, maybe some integration testing, then perhaps an independent team doing system testing, and maybe end users or clients doing acceptance testing. Different levels bring different benefits. But independence, the source stresses, shouldn't mean unfamiliarity. Testers still need to understand the software.
Wow. Okay. We've covered a huge amount of ground here, really dug into these fundamentals.
We really have, from defining what testing actually is and isn't to why it's so vital.
Yeah, understanding its value, how it connects to debugging and QA, those 7 core principles.
The whole process, the activities involved, the testware you create, the importance of traceability, the different roles.
And wrapping up with the skills needed and different team approaches like independence. It's a lot.
It is. It provides a really solid framework for thinking about software quality. It shows it's a complex, thoughtful, skilled discipline, not just an afterthought.
It definitely makes me appreciate what goes on behind the scenes when my apps actually work. And hopefully for you, listening, understanding your fundamentals kind of demystifies a really critical part of how the technology we all rely on gets built.
And thinking about those principles, especially maybe number 7, the absence of defects fallacy.
Right, the idea that just meeting the spec isn't enough.
Exactly. And the importance of validation, making sure you built the right thing for the users and the business. It kind of begs a question, doesn't it?
It is.
Well, if even technically perfect testing against the specifications isn't enough to guarantee success, how much does your perspective as the actual user, or as someone with a real stake in the software's outcome, how much does that perspective need to be part of the testing process for software to truly succeed in the real world?